Dear all, welcome to the video presentation of assignment 3 of AI Planning for Autonomy, Team 23. Azil, an engaging board game, involves players taking turns to draw tiles from factory to fill their game board. Talking with strategy, the game is a delicate balance of offensive and defensive strategies. Therefore, to design an AI engine, it requires the ability to handle game's complexity, uncertainty, and randomness. We start from researching the application of AI techniques in board games. With only a few search, we have found the significance of Monte Carlo tree search and minimax algorithm. However, directly apply this to method can be quite complex. We choose to begin with a more fundamental algorithm, which is standard queue learning. This algorithm is pretty straightforward. We apply the queue table to store a value for every state action pair, iteratively update the queue table, and extract the best action. In the experiment, the performance of our original queue learning is unsatisfied due to the lack of state action pairs revisiting and queue value updating. It can barely beat the greedy engine, and the win rate against random is not that well. Then we simplify the state action representation in the queue table. What we do is only collecting the pattern layout as well as the number of tile grabbed to the pattern line. Now our simplified queue learning agent is able to outperform the greedy engine and have nearly 100% win rate against random. However, our further implementation of n-step reinforcement learning actually gives a negative impact, regardless of the choice of n value. We reckon it might be the imitation of the queue learning algorithms. As a result, we would like to conclude our exploration now and move to MCTS, a more advanced method.
Our team decided to implement Monte Carlo tree search due to its wide range use in notable AI applications such as AlphaGo. And the success of AlphaGo underlines the potential effectiveness of MCTS in complex games. Initially, we implemented the basic component of MCTS, including sex selection, expansion simulation, and backpropagation. The first simulation strategy we used was random selection, aimed to expand the search tree to explore as many possibilities as possible. As Azul is a zero-sum game, we opted for a defensive approach, utilizing the win rate as our reward function instead of based on scores. As seen in the tables with various parameter adjustment, MCTS shows satisfactory win rate against greedy, random, and original minimax algorithm. However, as the implementation and optimization advanced, MCTS fell behind our optimized minimax. Future improvements can address the noticed discrepancy. Rather than use the random simulation strategy, we could use a more powerful in the future. Additionally, our win rate search could be refined by introducing a tiebreak function to better differentiate actions with the same win rate.
Let's move to our algorithm we use in the project, Remax. Remax is our decision-making algorithm for maximizing and minimizing pair used for our turn-based game. We optimize Remax with alphabet pruning and action update. Alphabet pruning reduces competition by excluding unlikely range and enhances efficiency and allows the AI to looking further ahead in the game. Action modeling soft action heuristically, rarely promising move first, enable more pruning and speed up the algorithm. Let's take a look at the top. Instead time growth at depth increase. Notice significantly less time growth for alphabet pruning and direction, especially at higher depths. However, beyond a certain depth, competition becomes too large and performance decreasing, particularly with more action. Minimax has limitation give our game humans cognitive demand. It often cannot fully use this time, even if we use iterative deepening depth first search. DDI as to control the search depth. Improvement is marginal due to the competition imbalance. Future improvement lie in dynamic weight assignment to the score function, adapting our strategy towards game state. It involves adjusting score earlier on and maximizing the loss nodes to get and this approach while complexity present more opportunity for AI development. In summary, despite minimizing limitation of the shared testing, possible improvement like dynamic weight assignment present a promising opportunity. Let's take a look at the final performance and the reference. Thank you.